finally at 15c. So for 15c, we're looking at h of x equal to 3x to the 5th minus 5x cubed. Again, this function is defined everywhere, so I don't have to worry about, whatever the domain might imply about this. I apply the first derivative to this function, I get 15x to the 4th minus 15x squared. I set this equal to 0. I can factor out 15x squared. I'm left with x squared minus 1 equal to 0. So this is 15x squared times x minus 1 times x plus 1 equal to 0. And this gives me either x is equal to 0 or 1 or negative 1. So this breaks the real number line up into the interval from negative infinity to negative 1, from negative 1 to 0, from 0 to 1, and from 1 to infinity. All right, so now I'm going to choose a test point from each of these guys, negative 2, let's say negative 1/2, 1/2, and 2. And I'll do a table this time because I do have a lot of factors flying around. Let's see. So again, my numbers are negative 2, negative 1/2, plain old 1/2, and 2. My factors are 15x squared, and all of these are positive when I plug these guys in, because 15 is positive and x squared is always positive. X minus 1, negative number minus 1 is negative, so these first two guys are negative, and 1/2 minus 1 is also negative, 2 minus 1 is positive. My other factor is x plus 1, negative 2 plus 1 is negative, it's negative 1. Negative 1/2 plus 1 is positive, and 1 plus any positive number is also positive. So those are positive. So at the end of the day, my first derivative, h prime of x, is positive times negative is positive, positive times negative is negative, positive, negative, positive is negative, and all the way down positive is positive. So this tells us that it is increasing on from negative infinity to 1, negative 1, and from 1 to infinity, and it's decreasing on the interval from negative 1 to 0, and from 0 to 1. So in fact, it's actually decreasing the whole time from negative 1 to 1. Even though the derivative is 0, at 0, it just sort of flattens out, and then it keeps decreasing. Something like that. Anyways. All right, this also tells us from the first derivative test, where we have local maximums and minimums. The function changes from positive to negative at negative 1, so we have a local max, and from negative to positive at 1, so we have a local minimum. So let me just write that again. So at x equal to negative 1, since the derivative changes from positive to negative, that means that we have a local minimum. No, it changes from negative to positive, right? No, from positive to negative, local maximum. I think I said the wrong thing back there. Excuse me, this should be a local maximum. At x equal to 1, the derivative changes from negative to positive. That means that we have a local minimum. And just to be thorough, at x equal to 0, h prime of x changes, well, it doesn't change, it's negative, and it stays negative. So this actually means neither. Now if we applied the second derivative test instead, this is what we would obtain. The second derivative of our function is 60x cubed minus 30x. Yep. And if you were to plug in negative 1, h double prime of negative 1 would be equal to negative 60 plus 30, which is negative, and we have a local maximum. That's cool. H double prime of 1 is equal to 60 minus 30, which is positive, and we have a local minimum. That's fine. If I plugged in 0, notice that I got 0. 0 minus 0 is 0. And so the second derivative test is inconclusive. we would have to go to the first derivative test to figure out what's going on. The first derivative test says since the derivative doesn't change sign, then we have neither a local maximum nor a local minimum. Finally, let's figure out concavity. Again, our second derivative we just computed to be 60x cubed minus 30x. I'm going to set this equal to 0. I can factor out 30x, and I'm left with 2x squared minus 1 equal to 0. So either x is equal to 0, or that does not look like 0, or 2x squared minus 1 is equal to 0. Adding 1 to both sides, I got 2x squared is equal to 1. Dividing both sides by 2, I get x squared is equal to 1/2. And taking the square root of both sides, I get plus or minus. This is equal to the square root of 2 over 2. That's one way of writing that. So this means that I have to look at concavity between negative infinity and negative root 2 over 2, between negative root 2 over 2 and 0, between 0 and root 2 over 2, and from root 2 over 2 to infinity. So the points I can look at here are, say, negative 1. Here, negative root 2 over 2 is about negative 0.7, so I can look at negative 1/2, then I can look at 1/2, and I can look at 1. And these are the guys that I'm going to plug into my second derivative. Let me erase this calculation over here. And there we go. Great. And get back to the paintbrush. There we go. All right, so I plug these guys in. H double prime of negative 1, we already checked, was equal to, I guess I got negative 30, which is negative, so that means it's concave down on this first interval. Let's do D. H double prime of negative 1/2 is equal to, when you plug it in, you get 60, negative 60 over 8 plus 30 over 2. You can check 60 over 8 is equal to, I guess that's equal to, it's negative 7.5. So this is 7.5. In any case, this is positive, so it's concave up on the second interval. On the third interval, well, you know, it's really worth it to be able to apply various mathematical facts when trying to compute things, say. This is an odd function. It's a polynomial with only odd powers, so if I evaluate the negative of something I already know, here I'm evaluating h double prime of 1/2. I know h double prime of negative 1/2 is 7.5. This implies that h double prime of 1/2 is negative 7.5. That's negative. The function is concave down on this third interval. Similarly, h double prime of 1 has got to be the negative of h double prime of negative 1, which is 30, which is positive. So we're concave up on this last interval. Down, up, down, up. Fantastic. For all these problems for number 15, just for kicks, it's probably worth it for you to just sit down and try to graph what these things look like. All right. Oops.